counting t-cliques, worst case to average case reductions, and direct interactive proof systems, inspired by Goldberg and Guy Rothbaum, and Guy will give the talk.
Thanks, Greg. So this is going to be a much more boring standard talk than the previous one, and we can also see the disadvantage of the digital format as opposed to roll talk. So good. So this talk is going to be about various complexity aspects of the problem of counting small cliques in a graph. So we know that counting large cliques is hard, but if the cliques are of constant size, for example, if they're of size 3, then we're just counting triangles in a graph, and that's a tractable problem, though it's non-trivial, as you can see with this beautiful GIF that I found online, given a graph to actually count the number of triangles in it. So we can do it in polynomial time, certainly time n to the 3, say for counting triangles. In fact, we can do better. So the worst case time is known to be no larger than n to the omega, where omega is the exponent for matrix multiplication. That's for counting triangles. And in general, for counting cliques of size t, it's n to the omega to the power t over 3 rounded up. Okay, so it's a tractable problem. Worst case complexity grows very quickly with the size of the cliques. And the question is, what can we say beyond the worst case complexity of this problem? In particular, does this worst case complexity really represent how hard the problem is on typical instances in some set? And in particular, can we find a hard distribution? A distribution where, given a random graph drawn from this distribution, it's as hard to solve the problem as it is in the worst case. That's sort of a basic question about a very basic problem. There has been some work on this, in particular beautiful work recently of Ball et al., that works that show how to reduce this type of problem to a hard distribution over a different problem, which in particular might be a little bit more difficult. Here we're focusing on the question of hardness on average or average case complexity of the problem itself, just the vanilla clique counting problem. And that wasn't known before, but our first main result actually shows a worst case to average case reduction. So a particular explicit distribution for which counting cliques is as hard on average. So given a random graph drawn from this distribution, it's as hard to solve the problem with probability 3/4, probability over the choice of the graph and any randomness you want to use, as it is to solve the problem in the worst case. Okay, so in particular, the reduction runs in almost linear time. Remember, the input size here is n squared. N is the number of vertices in the graph. The reduction only makes a polylogarithmic number of queries. The distribution is very simple and can be sampled in nearly linear time. And in particular, this means that the worst case fine-grained hardness, whatever the worst case polynomial complexity of clique counting is, it extends also to the average case over this distribution up to maybe some polylogarithmic loss. So the reduction gets a worst case instance and is given a solver that solves, so given a solver that solves over the distribution with probability 3/4, it calls the solver a polylogarithmic number of times. So that's a polylog possible overhead.
It's a Turing reduction.
Yes, yes. So that's for solving with probability 3/4 over a distribution. If you're a cryptographer or you like your hard problems to be even harder, then we also have a worst case to rare case reduction, showing a distribution where it's hard to solve even rarely. So hard to solve even with probability bigger than 1 over polylog in this regime. So even that is hard. There's a little bit of a larger overhead, so the number of queries made by the reduction becomes almost n. Remember, the input size here is n squared, so n queries is a little bit less than a linear number of queries. So in particular, the worst case hardness extends also to the rare case, to solving rarely, with a little bit of an overhead, which comes from an n overhead, which comes from the number of queries. So that's our first result. The second result studies a different aspect of this problem, and we'll see that these two aspects are actually tightly or very connected. And the second aspect is, well, once we have a graph, maybe drawn from a distribution, and it's hard to count the number of cliques, if someone does this work for us and tells us that the number of cliques is y, ideally we would want a proof. So we have this suspicious verifier, and he wants to verify that the number of cliques or number of triangles is y without doing the work himself. And the way we'll prove it is using an interactive proof. So this verifier can be randomized. He can send challenges and get back responses from the person who solved the problem, this prover, and in the end should accept or reject, where we want an interactive proof and the usual notions of completeness and soundness. So the question here is, we actually want to run these proofs in the real world, so we want, ideally, a polynomial time prover. This is the notion of a doubly efficient interactive proof. We want the complexity of generating this proof, of computing the prover strategy in the protocol, to be polynomial time. And this problem has been studied. We have general purpose protocols that apply to clique counting. We also have several protocols that have been proposed specifically for this problem. But one question that's open is, can we actually have a reduction? Can we have a reduction from the task of proving that the number of cliques is y to just the task of counting cliques in the graph? So we don't just want any polynomial time prover. We actually want a prover whose work is not much more than simply solving the problem. And our second result actually shows such an interactive proof, so a direct interactive proof with, I think, an appealing structure. You can see the quantitative bounds on the slide. The important thing I want to tell you is that the prover runs in nearly linear time given an oracle for counting cliques in a graph. So if you give me an oracle for solving the problem, then I can also prove the value of a solution. The number of oracles calls here is also quasi-linear in n, so there is a little bit of overhead over the complexity of solving. Nonetheless, we have a direct reduction from proving to computing. And the proof is direct. It has an appealing structure, so every iteration reduces the verification of the number of t-cliques or t-prime cliques to using a round of interaction to verifying the number of cliques of a smaller size. So after a constant number of iterations of this type, we're down to a claim about the number of cliques of size 2. Those are just edges. And counting the number of edges in the graph, the verifier can do that itself in linear time. Okay, so two results, worst case to average case reductions, interactive proofs. Actually, there's a common theme in both of these, which is to take the vanilla problem we start with, just clique counting in a graph, and reduce it or re-examine it using weighted versions of the same problem, where either we have weights on the edges or we have weights on the vertices, and that's how we get both results. So in particular, to get the worst case to average case reduction, first we reduce the unweighted problem to a more complicated problem. That's not a lot of progress, but a more complicated problem where we actually put weights on the edges. And for that problem, we show a random self-reduction. Okay, so we do show that this so this gives a worst case, a reduction from the worst case of the unweighted problem to some distribution over the weighted problem. Results of this type, I mean, this is a new reduction, but these results of this type were known before. The interesting thing is that now we can actually take this very natural problem, just edge-weighted clique counting, and reduce it back to the original problem. Okay, so we got from the worst case of clique counting to some distribution over edge-weighted clique counting, and now back to this induces a new distribution back over the original problem. So that's how we get our worst case to average case reduction. The interactive proofs, we get them using a similar sort of methodology, but we use a simpler vertex-weighted version of the problem where the weights are on the vertices, the edges are unweighted. And the important property here is that the vertex-weighted problem has a downward self-reduction. So we can reduce from counting vertex-weighted cliques of size t to vertex-weighted cliques of size t minus 1. And we also have there a batch verification protocol. I'll tell you what that is. That gives us an interactive proof. That gives us an interactive proof where the work of the prover is proportional to the complexity of vertex-weighted clique counting. And then we show how to reduce. That's a simple reduction, reducing that back to the unweighted case. Okay, so that's basically how we get both of our results. We have 4 reductions. I want to tell you a little bit about each of them. Some of them are simple. Some of them are a little bit less simple. So let me first tell you about the weighted versions of the problem. So the edge-weighted version of clique counting puts a weight on each edge. Think of these weights. You can think of them as integers, but for the talk, I prefer for you to think of them as coming from a finite field, say of prime cardinality p. And a weight that's not in the graph, think of that as having an edge that's not in the graph, think of that as having weight 0, and an edge that is in the graph has some non-zero weight over this finite field. Okay? Now, for any set of t vertices, the weight of the set is the product of all the edge weights inside that set. So if an edge doesn't exist, its weight is 0, and then the weight of the entire set is 0. If the set is a clique, then all the edges have non-zero weight, and now the set has some weight that's not 1, it's something in the field. And now clique counting, once we know what the weight of a set is, clique counting is just summing up the weights of all the sets of t vertices. Okay, so notice the non-cliques have 0 contribution, the cliques have non-zero, the cliques in the graph have non-zero contribution, and that's what we're counting. Clearly, there's an easy reduction from clique counting without weights to clique counting with edge weights. Just put a weight of 1 for all the edges in the graph and a weight of 0 for all the non-edges, and now this quantity will be exactly the number of cliques in the graph. And the nice thing about this problem, now that we've moved to working over a finite field, is that this problem does have a random self-reduction, or worst case to average case reduction. And now that we're working over a finite field, we can look at this quantity that we're trying to estimate and notice that viewing it as a polynomial over our input, so the input is the weight of all the edges, and viewing this as a polynomial over the input, this is a low-degree polynomial. And for low-degree polynomials, we have, by now, a rich methodology and powerful methodology for worst case to average case reductions, worst case to rare case reductions. So given a worst case input W, for example, you can draw a random line through W, query t squared points on the line, and then either interpolate or decode depending on what kind of error rate you're trying to handle. Okay, so that's an easy, or by now, so the important thing is identifying this problem, and we see sort of a reduction from the worst case of clique counting to the edge-weighted problem. Vertex-weighted problem is even simpler. So now the set of edges is fixed. So the edges don't have weights. Either they're in the graph or they're not in the graph. The vertices have weights. And now for a clique, its weight, instead of just being 1 or something that it was before, is just the product of the weights of all the vertices. Okay, so a non-clique has weight 0 by definition. We're just counting the weights of cliques. And now the weights of every clique can have a weight, which is the product of the vertex weights. And again, we have an easy reduction from clique counting to vertex-weighted clique counting. Just give all the vertices weight 1, and now every clique contributes 1, every non-clique contributes 0, and so you're just counting the number of cliques in the graph. So the first idea, and we use this variant of clique counting for building interactive proofs. The first idea is that we have a downward self-reduction for this problem, so fixing the set of edges. If I want to count the number of cliques in a graph, for every vertex, how many cliques is it involved in? Well, the number of cliques a vertex is involved in is equal, the number of cliques of size t that a vertex is involved in is equal to the number of cliques of size t minus 1 amongst its neighbors. Okay, so if we just look at the graph induced, say, by vertex i's neighbors, if we count the number of cliques of size t minus 1 in that graph and multiply that by the weight of vertex I, that's sort of the contribution of cliques that vertex I is involved in to the graph. That gives us a downward self-reduction from counting cliques of size t to counting cliques of size t minus 1 on n different graphs, each graph induced by one of the vertices in the original graph. Okay, that's our downward self-reduction. We go from 1 instance of t-clique counting to n instances of t minus 1 size clique counting. And to build an interactive proof, the second idea we need is a batch verification protocol that can reduce the n smaller instances that we get. So it's an interactive protocol that reduces verification of the n instances, smaller instances that we get, to the verification of 1 instance of the same size. And this, I won't get into it, it uses ideas similar to the original interactive proof for the permanent, if anyone still remembers that. One thing I'll point out is that it's just one round of interaction. It doesn't use the sum check protocol, so fairly direct. Okay, so I've told you a little bit about these reductions and the properties of these weighted problems, and now in the remainder of the talk, what I want to do is tell you how we get back to the unweighted problem. So getting back from vertex-weighted clique counting is going to be very easy. Getting back from edge-weighted is more complicated, so I'll just sort of give you a sketch of that, and that'll give us both of our result. So in the first direction, the easy case, going from vertex-weighted clique counting back to the original unweighted problem. So we have this beautiful drawing here with these beautiful colors, and the idea is to simply blow up every vertex. So we are given a graph G with weights on the vertices, and we want to go to an unweighted graph. So we simply take every vertex in the graph and we blow it up to a cloud of, if it had weight 2 of 2 vertices, so whatever its weight was, we replace it with a cloud of vertices. The number of vertices is equal to the weight of the node we started with. Okay, so the blue vertex here blown up to 2 vertices in the unweighted graph. And then every cloud in itself is an independent set. And for every 2 nodes in the original graph that had an edge between them, we put a full bipartite graph between their clouds. Okay, so that's the reduction. You can see it in more detail if you want to read the slide. And you're all very clever, so either you see it immediately or you can think about it a little bit and see that the number of cliques, the number of weighted cliques, or the sum of weighted cliques in this graph is exactly equal to the number of cliques in this unweighted graph. The cost of the reduction, notice here, is linear in the weights. Okay, so if the weights are very small, I made my life easy and I had small weights in the drawing. If the weights are small, then we're only blowing up the size of the graph by a little bit. If the weights are large, then the graph is being blown up by a lot. So in particular, this means that we need to work, in all of our reductions, we need to work with very small weights or very small finite fields. And we can do that. I won't get into it in the talk. Okay, so that's the easy reduction. The less easy reduction, which is also significantly more expensive, is going from the edge-weighted variant, the variant where we have these weights on the edges, to unweighted, just vanilla clique counting. In particular, the cost of this reduction is exponential in t. But for us, t is a constant, so we can afford that so long as the size of the weights is small, so the size of our finite field is small. So the way we do it is we start from an original weighted graph, edge-weighted graph G. We want to produce an unweighted graph G prime. And the idea is that every set of t vertices in the original graph induces a number of cliques in the unweighted graph that's directly proportional to the product of the weights of all the edges between vertices in the set. Okay, so a non-clique induces 0 cliques in the unweighted graph. And a clique will induce a number of cliques that's directly proportional to the product of the edge weights times this easy to get rid of factor of t factorial. So if we can count the number of cliques here, the unweighted number of cliques here, we can immediately recover the sum of the clique weights in the graph we started with. That gives us our reduction back to the unweighted case. In a little more detail, the way we do it up is we actually place many, many copies of the original graph in this new graph, unweighted graph G prime. They're not exactly copies, but we'll see, but sort of. You can think of them as copies. So the number of copies is p to the factor t choose 2. That's where the blow up of the reduction, the big blow up in the reduction, comes in. Each of these copies, you can think of it as being indexed by a vector. And the vector has an entry for every potential edge in a clique of size t. So it has t choose 2 entries, and each of them is given a weight between, say, 1 and p, or 0 and p minus 1. And that's how each copy is indexed by such a vector. And now, without getting into too much painful detail, each of these copies has t independent sets. Each of them has n vertices, so 1 vertex for each vertex in the original graph. So that's in each one of these copies. There are no edges between the different copies, so we just need to think about each copy on its own in terms of how many cliques there are. And for any 2 of these independent sets, say the independent set A and B, where A and B are between 1 and t, we put an edge between vertex u and vertex v. If the weight of the edge between u and v in the original graph that we started it with, and possibly forgot by now, so if the weight of that edge in the original graph is larger than the appropriate index in the vector, the appropriate entry in the index vector of the copy we're working with. So the important thing, I mean, you can think about it again, think about it offline or look at the paper for the details, but the important thing is that the higher the weight of the edge between u and v, the more of these copies it will appear in. Okay, so an edge with high weight appears in many copies, contributes to many cliques. For example, if we are looking at a clique where the weight of all the edges initially was p, that clique will appear, this is not a constraint at all, so the edges of that clique will appear in all of the copies, okay, because their weights are p. They will always appear in all of the copies, and that clique will actually induce t factorial cliques in each and every one of the copies of the original graph that we've created. Okay, so in particular, the product of the contribution of that clique to the original graph was p to the factor t over 2, and indeed it contributes to all of the copies. If the weights of the original clique were all 1, then it will only appear in the first copy. Okay, and in every one of the other copies, at least one of its edges won't appear. So it only induces cliques in the first copy, and it will induce t factorial cliques in that copy, which is what we expect. So we've covered the two extreme cases, and hopefully you can interpolate between those two to see that the claim is always correct. Maybe not, but you can look at the paper. So I really tried to simplify. I brushed a lot of complications under the rug. In particular, one thing I want to highlight is when we actually want to reduce from the worst case problem to the rare case, where we sort of were outside the regime of unique decoding, if you know about these worst case to average case techniques, then things get significantly more complicated. And one thing we sort of conceptualize is this notion of a sample-aided reduction, a reduction from solving one problem in the worst case to solving another problem in the average case, and this sample-aided reduction actually gets random solved instances of the second problem. So it's a weaker notion of a reduction. We give the reduction some help. And using the methodology of Impoliazzo and Wigderson, we know that using such, or one can show that using even this weaker notion of a sample-aided reduction, if the problem is also downward self-reducible, which I showed you that the vertex-weighted problem was downward self-reducible, you'll have to believe me about the edge-weighted problem. But if the problem has a sample-aided reduction and is downward self-reducible, then we can get a worst case to rare case reduction. Okay. I'm running low on time, so I won't get into proofs of work, but they're a nice motivating application. And if I went into the slide, then I could say the word Bitcoin. So I said the word Bitcoin, and now I can move on. So to summarize, we have these new insights about the complexity of counting small cliques, the fine-grained complexity of counting small cliques in a graph. We have a hard distribution. We also have direct interactive proofs. There are obvious open questions like tightening the reduction, so getting rid of the factor of n that we have, both in the worst case to rare case reduction and in the interactive proofs. The worst case to average case reduction is tight up to polylog factors. Our hope, or maybe it's optimistic, maybe it's realistic, is that this is one particular problem where we could get real insights about the average case. It's a natural, well-studied problem where we could get real insights about the average case complexity of the average case fine-grained complexity of the problem. And maybe once we have this for one or two problems in the fine-grained world, we can get it for lots of other problems. So maybe we can get a better understanding of the average case complexity of fine-grained, these problems studied in fine-grained complexity more broadly, not just for this one particular problem. And then the last thing I want to say is that this work and previous works talking about average case hardness of fine-grained problems, the techniques for proving average case hardness seem to be very related and tied to sort of the algebraic view of computation that we have in constructions of interactive proofs. So this has been more implicit in past work, and it's very explicit here, where we're both getting worst case to average case results and interactive proofs together. I think it's interesting to explore whether there really is a general connection between these two notions, and I'll end here. Thank you. So the smaller the field, actually, let me also go back and say something about that. So the smaller the field, the less expensive the reductions, but also the less expensive the reductions, but working with smaller fields also raises complications. For example, we always want the field to be at least as large as the degree of the problem, as the degree of the polynomial we're talking about, so that bounds something about the primes we can work with. We also use Chinese remaindering in more ways than one. We need to use Chinese remaindering in more ways than one. One particular aspect that's often ignored when we talk about these worst case, average case reductions is that you're picking a prime, and then your instance, the problem you're trying to solve, actually has this prime that's embedded. That's part of the input to your problem. And what if now you're given you choose your prime very carefully, but you're given a solver that fails on that prime? So that's a complication one needs to deal with. And we do it using Chinese remaindering with errors. There are results on these lines that adds another layer of complication.
Okay, well, we're off to the coffee break.
Thank you. Okay. I don't know. Do you think it went well enough to sign? You tell me.